This video is looking at the graphs of exponential functions in the form y equals a number, times some other number to the power x. We have been used to looking at rules where you've got x in that position and the number in the power position. It's the opposite way around. These graphs are called exponential. Okay, the very basic one we can start off with is we make the multiplying number at the front 1, a, met a lots of times now, and the simplest base we can look at is base is 2. We could look at base 1, that gives us a horizontal line. So we're looking at where the base is 2, and we put the x values in. So if we put in, for instance, x equals 0, this becomes 1 times 2 to the power 0. 2 to the power 0 is equal to 1, so I put 0 and I get 1 out. So this graph has a y-intercept, but you'll note there's no x-intercepts. And the y-intercept there's 0, 1. If I put 1 into the rules, it becomes 1 times 2 to the power 1, so that's 1 times 2, and we get 2. If I put x equals 2, it becomes 1 times 2 squared, which equals 4. If I put 3 in, it becomes 1 times 2 cubed, which is 8. This value up here, put 4 in, is 1 times 2 to the power 4, which is 16. Look at the values here, so different values. If I put in negative numbers for x, we get very small answers. If you remember our work on indices, putting a negative number into a power doesn't create a negative answer, but creates a fractional answer. So here you can see when I put negative 1 into the rule, it becomes 1 times 2 to the negative 1, which is the same as saying 1 times a half, and that's why you get 0.5. Put negative 2 in, 1 times 2 to the negative 2 is 1 times a quarter, so I get a quarter. Once again, if I keep putting in very big negative numbers for x here, the answer gets closer and closer to 0. You can have a look here, when I put negative 4 in, it becomes 0.06. If I put, so the bigger the negative number I put in, the closer we get to 0. What happens out in this direction? The bigger the positive x value put in, quickly the graph starts increasing. You may have heard of the expression exponential growth, and that's exponential growth is where it increases very quickly. As I change the base, so we started off with 2 to the power x, let's look at 3 to the power x. Pink dotted graph is 2 to the power x. Now if we make it 3 to the power x, this point here is 1, 3. This point here is 2, 9. This point would become 3, 27. We can't see that. Let me just move the graph down a touch. You'll see it comes up as 3, 27. What's happened here? The new graph here is positive a third smaller, and so on this side of the y-axis the graph gets steeper. On this side of the y-axis the graph is flatter than to the x. So as I increase the base, now I'll go to 5 to the power x. You can see it's got lots more steeper there. This is what we talk about exponential growth. It increases very quickly. For a small change in x, we get a big change in y. This graph here you can see is a lot higher than 2dx, but the values on this side of the way are a lot closer to 0, a lot quicker. It's rounding off that the negative 4 is to 2 decimal places, we round off to 0. So let's increase the base right out to 10, and you see it really bends the graph up and makes it much flatter on this. You can see over here the original value was negative 1.5. On the new graph, on 10 to the x graph, it's negative 1.1 or 1/10. So as we increase the base, on the positive side of the y-axis, the graph gets very steep, but on the negative side it becomes very flat very quickly. So just look back through the bases, and you see the black line bends back towards that x to the power x, and as I increase the base it starts bending it up. Okay, that's the first part of the video. Next part of the video is we're going to look at changing the value of a. I think in your notes we start with y equals 2 times 3 to the x. The red graph is the graph of y equals 1 times 3 to the x. That's 2 to the x. This is the graph that we've got here in the rule, 2 times 3 to the x. And you can see that the graph is twice as high. It's been stretched up 2. Because this value here is 2.9, and now it's 2.18. So if I increase the value of a, let's go out to 3. It's 3 times as high. Then stretched, dilated is the correct term. So we go out to 5 times 3 to the power x. The graph has been stretched 5 times, because this point here was 1.3. It's now 1.15. When I put x equals 2 into the original rule, it was 1.9. Now it's up to 9. It's now 2.45. So you can see it gets very big very quickly. Over on this side, because we're stretching the graph from the x-axis, we're dilating. The black line is now sitting above the red line. We're stretching it away from the x-axis, but it still gets very close to 0 very quickly. We'll now look at the case where a is a half. Remember, the black graph is the graph listed here, and it's half as far away from the x-axis as the original 3 to the x graph. Remember, the pink graph is 2 to the x, so it's brought down by half, which is consistent with all the work we've done with changing the value of a. The next thing we investigate is if a is negative. So here we've got a is -1, and we can see, just like with all our other types of graphs, the graph has reflected in the x-axis. So let's change the base to 2 to the x. So the pink graph is y equals 2 to the x. The black graph is -2 to the power x. And the original point 1, 2 here now becomes 1, -2. This point here 2, 4 becomes the point 2, -4. The point 3, 8 becomes 3, -8. 4, 16 becomes 4, -16. Can't see that, but you can see the table there. And same thing happens here, that flipped over the x-axis, the points, but still getting very close to 0 very quickly. As I increase a, make it a bigger negative number, it stays reflected, and it just stretches it away by that factor. So here a is 5, -5, it's reflected over the x-axis, and it's 5 times further away from the x-axis as it is on the positive side. If you look at the table here, 2, 4, that becomes 2, -20. 4 times -5 is -20, so it's down here at -20. This point here, -1.5, that becomes -1, -2.5. 5 times further away from the x-axis. Alright, now you need to complete the worksheet and the questions from the work plan. Thank you.